Welcome back to Mechanics and Control of Robotic Manipulator. So last few classes we have seen forward kinematics and inverse kinematics. We have seen several example on the slide. So but I told like these things we can do it even in MATLAB based. So this particular lecture is going to talk about forward kinematic solution finding using MATLAB symbolic math toolbox. So I am not actually like promoting MATLAB, but we can actually like even do it this in several other softwares, but this particular course MATLAB we are going to use. So where the symbolic math toolbox we would be adapting. So where we can write the the DH matrix, what you call ARM matrix, and you give the DH table, then it automatically generate with the help of our own code. It is not like a robotic toolbox. So robotic toolbox also will do the similar sense, but I want you to understand the behavior. So we would be using basically like a simple symbolic math code, and we would be writing our own MATLAB code. So in the sense, if you give a DH table and the ARM matrix, it would be finding the entire forward kinematic solution along with what you call position vector and individual normal sliding and approach vectors and all. So this is the whole idea. If you get this, then even we can actually like use the same MATLAB for solving the equation, then we can actually like even find the inverse kinematic solution as long the sufficient and necessary conditions are fulfilling. So in that sense, what one can see, so we would be taking two such example. So initially we start with the planar RR serial manipulator, then the other one is actually like spatial RRR serial manipulator will be taking. But as I already mentioned, we are going to use MATLAB symbolic math toolbox. It's actually like very small set of tools only we are going to use, only symbol and substitutions. So these two only we are going to use. So for that, what we are taking first case. So we are taking as actually like 2R serial manipulator. I hope you remember what is the DH parameters. So if I actually like recall this, so this would be having alpha 0 is 0 and A0 is actually like again 0. But when you come to alpha 1, that is also 0, and A1 would be as equal to what you call L1. So similar way you can come to alpha 2 0, and A2 is actually like L2. And the other side if you come, so this is actually like theta 1 and this is theta 2. So that is what we get. So we will go to MATLAB window and then we will see. I have already created a file for you. I will be explaining how I have actually like generated. So this is actually like a DH transformation matrix and direct kinematics of a serial robot. This is the general code. The same code can be used for any serial robotic manipulator. That is the whole idea. So here the notation we are going to use or the frame assignment, all we are actually like used based on the course which we have covered, like mechanics and control of robotic manipulator. What that specific class I am putting here, because this particular matrix what we are going to use as a DH matrix is the non-standard one. So if you want to use the same thing for the standard one, then the ARM matrix what I have written here, so this need to be modified. Okay. So what that means, so here I have written as a mix of alpha I minus 1, AI minus 1 and theta I and di, although I did not label it here, but that is the idea which change. Okay. So the general Danavet-Artenberg transformation matrix here we use as the non-standard one. Let us go to the code what exactly it is written. So the initial code is actually like very same. So clearing the memory, or you can say clearing the workspace and closing all the window which is figure windows open and clearing the command history. Then we are creating 4 symbols mainly for actually like denoting the kinematic parameter, what you call alpha I minus 1, A I minus 1, di and theta I. So which are actually like I am writing without any you call suffix, in the sense without any frame arrangement. We are writing A, alpha, theta and d. That is what we have written here. You can say alpha, d, a, theta. So in addition to that, so based on the DH table, like there would be A1, A2, theta 1 and theta 2 would be coming in this case. But what we know additionally, these all are real variable. So initially I did not mention it's a real or complex, but here, so whatever you have got, so theta 1, theta 2 and A1 and A2, all I am writing as what you call, so the symbols which are real symbols. So now in that case what we can see, so how many frames we have used? So there are 4 frames. because it is a 2-axis robot. So, one end effector frame and 0th frame. So, when we are writing the number of transformation matrix, we usually ignore the 0 because we do not have any transformation before that. In the sense, transformation matrix of 0 with respect to -1, we normally will not do it. So, that is why you can see number of joints, in the sense number of frames, excluding 0th joint or frame, is number here is 3, because 2 axis and 1 end effector point. So, in the sense n equal to 3. So, now what we are writing? So, the DH table we are writing. So, the DH table would be having 4, you can say, columns. In this case n is 3, so 3 rows. So, in the sense what you can see, like this is actually like alpha a I minus 1, so you can say alpha I minus 1, in the sense all alpha 0 because it is in planar, and a0 is 0, and a1 is as a1 and a2 as a2, and theta 1 is there, which is active variable, theta 2 is another active variable, and theta 3 is, it is passive, so it is 0 in this case. So, similarly, when you come to what you call the final D, so there is no translation along Z1, Z2, Z3, so all D's are zeros. Okay. So, this is what? This is equivalent to alpha, this is equivalent to A, this is equivalent to theta, this is equivalent to D. So, in this DH table, it is actually like everything we have written. So, now what we are doing? We are bringing the non-standard, what you call transformation matrix, in the sense ARM matrix, we are actually like bringing it. So, now this is the non-transformation matrix. So, you can actually like see it here. So, this is actually like non-standard ARM matrix. So, we have actually like used this. So, now what we can actually like do it? So, we are actually like getting the one simple briefcase. What that mean? So, we are actually like creating a bigger stack or rack. So, this rack would be consist of n cells. So, here n is actually like 3. So, each cell would be represent individual transformation matrix. Now, in that sense what we are trying to create? We are trying to create a cell of A which is having 3 cells inside. So, what that means? So, the first cell corresponding to transformation matrix 1 with respect to 0, second cell would be corresponding to transformation matrix of 2 with respect to 1, and the third cell will be correspond to transformation matrix of 3 with respect to 2. So, in the sense we are actually like making a rack. So, that rack formation only we are calling as a cell 1 comma n, here n is 3. So, we are actually like making it. So, number of columns is 3, in the sense it is actually like in horizontal, the rack 1, 2, 3, like that it is going to be there. So, now once you create the cell, what we are trying to do? We are trying to substitute the, you call DH parameter inside the ARM matrix. So, for that we are taking actually like for loop, because there would be 3 rows. So, each row would be corresponding to, you can say, substitution which end up with corresponding transformation matrix. So, for that we are actually like substituting first alpha, then A, then theta and D. We are actually like substituting into the DH table. So, you can recall this is the DH table. So, we are taking the DH table value corresponding to A, corresponding to alpha, corresponding to theta and D. So, this we are going to substitute into TDH. So, that is what we are actually like going to do. You see, initially we have, you can say, equate alpha, A, theta and D corresponding to the rows. Okay. So, corresponding row in the 1, in this case first time, first row, first column, second column, third column, 4 would be denote alpha, A, theta and D. Once you get this alpha to D, then you can substitute these variable into TDH, in the sense your ARM matrix. Now, what it will come? The first cell will fill with the first DH table, first row of DH table, that will give T01, okay, in the sense T1 of 0. The second iteration, it would be second cell, that would be T2 of 1. The third cell, that would be T3 of 2, that we would be getting. So, once you get what you wanted, so individual transformation matrix is there, then you can actually like post multiply and get the final solution. So, for that we are actually like displaying it. I will show you it in the output. So, we are actually like trying to first start the iteration again. So, for that we are taking, because you have n steps, right. So, we do not know like how it start. So, we are starting T as a simple identity matrix. Now, I am post multiplying one by one. So, what I am doing? The first initially I take identity matrix, the first cell is post multiply, okay, that I am simplifying. Then the second iteration, the T become A of 1, then that is post multiply with A of 2. Then the third iteration, that would be post multiplied with A3, but that pre multiply with, you can say, T0 to 2. That is what the equation. So, in the sense what you can see, so this is the individual matrix, and the output is actually like final, you can say 0 to n, the n is here 3, and the last column, first 3 rows is actually like position vector, and the first you can say column would be related to normal vector, then the second you can say column related to sliding vector, the third column would be related to approach. Okay. So, now if I run this, so what you can actually like get it, so you will get the output. So, you can actually like see here. So, now you can see like what it has given. So, first it gives the DH table. Okay. So, then it says that the direct kinematics of a planar serial RR manipulator is happening, and simplification may need some time. The number of joints is here 3. So, in the sense you would be expecting 3, you can say transformation matrix T01, okay, then T12 and T23. So, now if you post multiply, finally you will get T0n, so which is actually like in this form. Okay. So, you can actually like see this is the form. So, you can take individual, so in the sense the position vector. So, the position vector what we used to get, so A1 cos theta 1 plus A2 cos theta 1 plus theta 2. So, it is actually like order is changed, but the output is same. So, in the sense there is a sign case, that would be your what you call the y vector, or you can say y value, this is x value, this is y value, end effector position, and this is your normal, and this is actually like your sliding, and this is your approach. Now, once you obtain what one supposed to do, so you have to cross check whether the home position is matching. So, for that we take here. So, what we are trying to do, the home position in the sense the theta 1 and theta 2 we substitute into 0. So, in the sense what we are trying to do, so I am putting theta 1 equal to 0 and the theta 2 equal to 0. Okay. So, I am substituting that. So, now if I substitute, what you will get, so it will give the home position, you can actually like find it. So, now you can see that the x displacement is A1 plus A2, that is matching with our previous attempt with a straightforward forward kinematic relation without, you can say, MATLAB, and the normal would be 1 0 0 and slide would be 0 1 0 and approach in the sense. So, you would be getting an identity matrix. So, because your z axis is parallel to your z3 axis parallel to z0, your x3 is parallel to x0. So, in the sense you would get the orientation matrix as identity. So, that is what you are getting it. So, for example, you can see, so it is getting identity matrix and x displacement only there, y is 0 and z is again 0, right. So, now you can see that this is the way you can actually like use the MATLAB is one of the aid, and we have actually like obtained. So, now the same thing can be used even for other benefit. So, for example, I have already written a code for RRR manipulator. So, before that I will come back to this slide set. So, you can see like what we can actually like see. So, you can actually like find this is the RRR manipulator. So, we have already found the DH table. So, this DH table, if I put it inside the what you call the new code which I have written. So, I will modify the n axis actually like 4 and I replace this DH table. So, I will get the forward kinematic solution. Can I check that? Yes, I will actually like check this. So, you can see like now what I did, I have actually like modified this. So, now this is actually like written the same thing, but what I am trying to do. So, here you can see like there is A1, A2 is replaced with A2 and A3, because your DH table does not have A1, but A3 is there. Similarly, you can see that there is a displacement on the z axis. So, D1 is there, and here actually like again it is actually like a 3 axis system. So, theta 3 also there. So, these all are real variable. So, now the number of joints are actually like 4. Okay. So, now the DH table whatever we have seen in the previous slide. So, this is directly I substituted here, right. So, now if I run this, what I will get? So, I will get a transformation matrix individual, and then finally, I will get the final position vector orientation matrix all, right. So, can I actually like run this? So, I can actually like run now. So, you can actually like see. So, it takes time. Okay. So, in the sense I will just run this. So it is actually like a run now. So you can actually like see this is the final, you can say, output. So this is the final output of T01. Anyhow, I would be sharing the same code with you in the lecture material. You can also run and cross verify, but now you can see that this is the individual transformation matrices, okay, T01, T12, T23, T34, and you can actually like see this is the position vector. So you can actually like see the position vector is exactly matching what you have obtained in your, you can say, straightforward relation which you have obtained in the previous lectures, and this is the normal, and this is the sliding, and this is the approach vector. So now as usual we need to cross check whether the solution is actually like matching or not. So for that what you can do, you can take the theta 1 equal to 0 and sorry, so theta 1 equal to 0 and theta 2 equal to 0 and theta 3 equal to 0. Okay. So now in that sense what would be the home position? So you can actually like see home position says that in the x axis A2 plus A3, y axis 0 and z axis D1, and the orientation you can see x4 and x0 is parallel. So in the sense 1 0 0, but z4 is actually like parallel to y4, in the sense the third vector would be 0 1 0, but the second vector which is actually like y4 is coming downward, in the sense 0 0 minus 1. So that is what we can actually like expect. So we can actually like run that. Okay. So if I run this, what you can expect? So in the x axis it would be A2 plus A3. So we can actually like check, right, and y axis 0 and z axis D1, and normal is actually like 1 0 0, that is what we have also checked, and sliding is 0 0 minus 1, that is also cross verify, and approach is actually like 0 1 0, that is also cross verify. In the sense your, you can say, home position is matching with your frame arrangement, in the sense your DH parameters are right and whatever you obtain the forward kinematic solution is right. Okay. So as I already mentioned, the inverse kinematic direct closed form solution using MATLAB may be possible. In fact, it is possible. Only thing, the complexity is actually like very high. I don't want you to actually like end up with that way. Very simple example I will show you here. So I can actually like write symbols. Okay. So I can write symbols are actually like theta 1 and D2, which are real. Okay. So even I am writing as a x and y also real. So now you can see, right, I am actually like writing it. So I'll write it as actually like x is actually like, you can write so what is that, D2, so cos theta 1. Okay. So this is the way. Y is actually like a D2, you can say sine theta 1. You can actually like recall the RP manipulator we have run, right. So now this is actually like, you know, already forward kinematic solution. Now this kinematic solution is given, can I find inverse kinematic solution? So for that what we are trying to use, so we are trying to use the solve command. So what we are trying to say, so A and B are the final result, which is equal to theta 1 and D2. I am just using a random variable. I am solving two equation. What equation? So D2 sine, okay, theta 1 equal to x. Okay. So since I am writing equation, so equal to like this. So then D2 sine, sorry, that is, so this is sine, that is cos. Okay. So I will correct it. So this is equal to y. Okay. So this I will correct it as cos. So I have written as these two equation, and what I am trying to solve, I am trying to solve theta 1 and D2. Okay. So now if I actually like put this, so it will actually like give the solution, right. So why it is actually like giving 0 0? Because we have already found that the theta 1 is 0. So now I am actually like substituting this. Okay. So first I am clearing everything. So now I am actually like this one. So now I am actually like using this relation. So now I am actually like finding it. Okay. So now what you can see, I got the final solution. So the final solution says that the theta 1 is, so 2 times of A tan inverse, this is tan inverse of x minus, so this is actually like x squared plus y squared, which is actually a square root divided by y, right. This is actually like one solution. If I put minus, that is another solution. So how this is solved? So it is actually like solved with the help of what you can see. So x is actually like d2 cos theta 1, y is actually like d2 sin theta 1. So it has actually like solved square and add, so it will give d squared. Then you can actually like say that, so x minus, in the sense it used half angle quantities, in the sense it used sin theta as actually like in the form of tan theta by 2, and cos theta also tan theta by 2, that relation half quantity, and then get it. So in the sense the same thing actually like can be used, but what we have used, we have straightforward written as, so theta 1 is tan inverse of, so y by x, right. So the other one is actually like a simple square root of x squared plus y squared whole square root, you can take it, that is what d, right, d2. So that too like we will take plus solution, because the minus solution will not be possible, because it cannot go beyond. So that is what the whole idea. So in that sense you can actually like see that the inverse kinematic solution also can be found using MATLAB, but it is actually like a slightly tricky. But if you give a numerical solution, okay, so numerical solution in the sense, for example, I am actually like using it, so instead of this, so I am saying that I will just make it this clear all. So I am putting clear all. So now the same equation I am actually like putting some value, okay. So this is 1 and this is actually like probably 0. So in the sense what you can expect, the d2 would be 1 and theta 1 would be 0, right. So we will actually like get it or not. So now it is still defined as a symbol. So it is actually like, sorry, so it is, so you can actually like see that the theta 1 is 0 degree and d2 is actually like 1, right. Like that you are actually like getting a solution. So like that you can actually like use even MATLAB for solving the inverse kinematic solution, but I don't recommend that. So if you want to actually solve the inverse kinematic solution, so better you can go with a numerical method. So the next lecture would be talking about numerical method. So until then, thank you and see you. Bye. Take care.